Hi guys, welcome back to my channel, and today I'm going to be talking about dynamic programming. So, what is it? Well, to be honest, dynamic programming is a pretty bad name for the technique because it has nothing to do with being dynamic. Obviously, it is programming, but dynamic doesn't really fit the bill. So, now let me tell you what it is. And let's start with an example. Before on this channel, I have talked about the Fibonacci series and how to code it. So essentially how the Fibonacci series works is you're given a problem, calculate fib of n. And the initial mathematical problem is you start with two values, 1 and 1. And as you go forward, the next value is the sum of the last one. So the third value would be 2. The next value is 3. Next value is 5. Next value is 8, and so on. So if I ask for fib of n, I'm asking for the nth. And following the classic programming indexes, it will be like this. So fib of 0 is 1, fib of 1 is 1, fib of 4 would be 5, and so on. So, how do we code this? There's many good videos and articles about this, and there are some good ones on my channel, which I'll link below if you'd like to know more about this specific problem. But let me skip to the solution. The solution is to simply implement it in blatant terms. The mathematical formulation for this problem is that fib of n equals the fib of n minus 1 plus the fib of n minus 2. In this case, you're not starting from the beginning, you're actually starting from the end. So let's say we wanted to calculate fib of 8. Then first, we'd have 8. 8 would call 7. We start with 5, of course, because it's the indices. So 5 would call the fib of 4 and fib of 3, which would then call fib of 3 and fib of 2, which was then 3 would call fib 2 and fib 1, and this would go down until we hit our bottom case. Now, what would be our bottom case? If we know these two values over here, so basically we know what fib of 0 would be and fib of 1 would be, so we can have those as a bottom case. We can say that if fib of 0, we'll define that we know it, that both of them are 1, as in the problem, and once we hit it, like over here, we just return 1 with no extra calculation. So, here is how you implement it in blatant terms. You use something called recursion. So here we have a function fib of n. We're checking if we reach the edge case, which is n equals 0 and n equals 1, then we'll just return 1. And otherwise, we do the exact same thing we saw earlier. And here in the main is just some things to make the example look nice and take input. So let's run this. I'll compile it and let's go. So I'll enter n and let's try 1. Fib of 1, as we know, is of course 1. So let's do this again. What is fib of 5? Fib of 5 is 8, as we've calculated here. Now let's check what is fib of 6. It's 13. All right, let's check it. Fib of 6 would be 5 plus 18, so that is in fact 13. It's correct. Now, if you try to run this for bigger test cases, you will see that it's very, very slow. And there's a very good reason for that. If you look at this graph at this tree over here, which is the tree of the calls, you can see an interesting problem beginning to arise. We can see that fib of 3 is called here, right? Twice. Now, this is a fairly small test case, and 3 is being called twice, which means that since 3 calls 2 and 1, those will be called twice. And this will keep on bubbling down. And this is a very big problem because that means we're doing a lot of non-needed recalculations. Here we have 3's. If you go another level, if we write everything down, you have to do 1 a lot of times, 2 and 2 a lot of times. See, 1, 2, 3, 4, 5, and 1, 2, 3 times of 2. And this problem will just get even bigger and bigger as we move up the test cases. So, how do we solve this? Well, the answer is actually quite simple. We just keep a record of all the things we've solved before. And this is called memorization. Now, this is a interesting term, which if you haven't heard of DP before, you might not know. But essentially it is that you keep a memo or a little note of the answer to every calculation of the function, so you don't have to recalculate it. So if you use memorization, then when the first time you calculate 3, you save it in what we call a memo. So our memo of 3 would be 3. And now when we go here, we don't have to call all of this again. We can simply look it up from the memo and be like, okay, this is 3, and end it there. So this way, we won't repeat anything, and this becomes vastly, vastly faster. So let me show you this is the code for that. It's plain and simple. Just 2 lines are added. All I have to do is add an else if that checks if it's in the memo, and of course, a memo. Now, if we look at it, everything works the exact same, except much, much faster. Let me show you a bigger test case. If we try to find the 100th Fibonacci number, this is actually so big that it will overflow. But if we try to use, here we try to use this, it may not even finish. Look. The other one happened instantaneously, but this one is not returning. And that is because it's just redoing so many calculations that it takes this long. And I will actually Control-C this because it will not finish. I may have to leave it for weeks or at least a couple hours for it to finish. So now, this is the basic premise of DP. You implement a pure bare bones solution, like brute force, and then you use memorization to optimize any recalculations. Now, there is one different way of formulating a DP solution other than using memorization, and that is called the bottom-up solution. So in this case, we start from 8 and then we go backwards. And this is called top-down because, of course, this is the top and this would be the bottom. So, as you might be able to deduce, a bottom-up solution just goes from the bottom up. So, let me show you how it's done. Basically, what you do is at the beginning, you don't exactly know what you will need to calculate in the future. Of course, this is Fibonacci, so you know that you'll have to know everything before it, but in different kinds of problems, that might not be the case. So here, we might need to do some calculations that are some extra calculations, but this may be faster in some situations because in recursion, you have to let the compiler handle pointers, the stack, and all that stuff. But in this case, it's just a simple iterative approach. So how do we do it? First, we'll do fib of 0 and fib of 1 at the beginning, which we already know, and will again be set. So how do we add this? So how will we do this? Well, to initialize these, we will put in our memo, right? That's how we do memorization. That memo of 0 is equal to 1, and that memo of 1 is equal to 1, because that's what we're starting with. Now, we'll do a for loop. In this case, it'll start from 2, and it'll go all the way to n. And what we do is each time, and let's say this is represented by I, we know that the memo of I, again, implementing it straight from the mathematical perspective, is equal to memo of I minus 1 plus the memo of I minus 2. And this is exactly all you need to do, because since you're doing it bottom up, once you get to 2, you already know the answers of these. And once you calculate 2, you know all the answers for 3, and so on. So let me show you the code. Here it is. Just to tidy up the code, I've put it in a different function, and you can see it's very simple. Here, we set the initial values, which are 0 and 1, as we discussed earlier, and then here we go from 2 all the way to n, and we just put this part. Now, we will just return memo of n, because it's already been calculated. So, let's see if this works. Try it with 1, good. Try it with 5, good. Try it with 6, that looks great. And now let's try with 100 again. Now, you can see in both of these situations, it's negative, which is obviously not right. The only reason is because actually the fib of n is so big, it's overloading the integer, the maximum for the integer value, which it then goes to negative. But this just goes to show that it's much, much faster than the normal way. And in some cases, if memorization doesn't work on a problem, then using bottom up can squeeze out just enough milliseconds to get it accepted, and vice versa. So, to sum it up, DP is simply a way of optimizing brute force solutions to a problem by ensuring that there are no repeats. Alright guys, thanks for watching. I hope you enjoyed the video. Please like and subscribe if you want more, and I'll see you next time.